In this video, we're returning to binary to cover a loose end that we haven't discussed. That's the question of how to represent negative numbers. All the integers we've worked with so far have been 0 or positive. Can you even represent a negative number in binary? If so, how? Let's think how we might approach that problem with an example. We know that the decimal integer 9 is represented 1001 in binary. Now, how might we represent negative 9? We can't just stick a minus sign onto 1001 because computers won't know what to do with it. They only recognize 0 and 1 and no other symbols. Well, one approach would be to change the way we do binary representation in the first place by adding a bit onto the end of every number that holds information about its sign. For example, we could take 1001 and make it 01001 if we mean positive 9 and 11001 if we mean negative 9. Now that would certainly distinguish 9 from negative 9, but first of all, it would make negative 9 indistinguishable from 25 in binary. And even worse, it would mess up the way we do arithmetic, because if we added these two together, we were supposed to get 0, but instead we get this, which is definitely not 0. So we'd have to completely redo all the algorithms for arithmetic we've built up, and that just seems like a lot of work. But it's not a terrible idea to add a bit to a number to indicate its sign. We just need to do this in a way that makes it workable with all the arithmetic we've seen. Now, it turns out there are multiple ways to do this, but the most common one in computer science is called 2's complement. Here is the process for how to write a negative integer in binary using 2's complement. To begin, we first have to predefine the number of bits used to represent any integer. This is built into the hardware choices of computers. For example, when you hear of a 64-bit or 32-bit operating system, that means that the system is designed to handle chunks of data of that size, 64 bits at a time or 32 bits at a time. In an 8-bit system, information would be handled in 8 bits at a time. So in that case, the number 9 would not be 1001, but 00001001. The largest number an 8-bit system could handle is 8 ones, which is 255 in decimal. Once we know the number of bits used to represent an integer, here's how to represent a negative integer. We start with the positive version of that number. For example, we saw 9 is 00001001. Then first we invert or flip all the bits from 0 to 1 and 1 to 0. Now add 1 onto this. The resulting bit string is the 2's complement binary representation of that number. For example, we saw positive 9 is 00001001. To represent negative 9, first flip the bits to 11110110. Then add 1 to get 11110111. And that's the 2's complement representation for negative 9. Notice that when we add these two, we don't actually get 0 like you might expect. Instead, we get 2 to the 9th power. But since we're in an 8-bit system, this truncates to 0. Thanks to the 8-bit system, therefore, we do end up with 0 like we should. This makes 2's complement consistent with the rules of addition that we already have. Now you do the next example using the 8-bit integer 199. In binary, this is 11000110. Follow the steps for 2's complement to write negative 199 in 2's complement form. Pause the video and work that out, and again, don't worry about mistakes. So to get negative 199, we first take 199 and flip its bits to get 00111001. Then add 1 onto this to get 00111010. You may want to go off to the side and do the addition separately since there's some carrying involved. This gives us negative 199 in 2's complement form. You can check this if you want by adding these two binary strings together, and you'll see that, again, you get 2 to the 9th power, which in an 8-bit system is just 0, which is what you're supposed to get. So why is this method called 2's complement? Well, the 2 comes from the fact that we're in base 2, or binary. The complement comes from the bit flipping. As we're going to explore in a later module on logic, flipping bits like this is akin to changing a switch from off to on or vice versa, or more accurately, it's like changing a logical value from true to false or vice versa. The opposite of the truth value in logic is called its complement, and that's the first step in the process. And as the examples we saw hint at, when we add a number x to its opposite negative x, we always end up getting 2 to the n plus first power if we're in an n-bit system. So the x and negative x are complementary in that sense. So in this video, you learned how to represent negative numbers using 2's complement, which is a way of writing negative numbers that works with the binary arithmetic we've seen throughout this module. That's the end of this module on integer representation, so congratulations on a lot of well-done hard work. Next, we're going to explore the world of logic and see how computers use logic to operate.